Alright, so continuing on from where we left off in the previous lecture, we will look at the Schrodinger's equation in quantum mechanics. We basically introduced it in the previous lecture, but from this point on we will see how to actually use the Schrodinger's equation and what it can tell us about the behavior of the wave particle in certain systems. So, the first example or the application for our Schrodinger's equation would be through an example which is quite popular and which is something called as a particle in a one dimensional box. Okay. And what we have here is the profile of the potential versus the distance. Now, although we keep mentioning the word potential, okay, and I do keep using the term potential, I would like to emphasize that this term in Schrodinger's equation, which is minus h square by 2m dou square psi by dou x square plus v psi is equal to E psi, this term corresponds to the potential energy. So, we are equating energies. Okay. So, we are saying that this is the kinetic energy, this is the potential energy, and that is the total energy. Okay. But since the potential is the equivalent of the potential energy, I would sometimes use the term potential while talking about these concepts. So, in this case we now have a potential profile that looks like as shown, and the particle or the wave function exists somewhere in this region from x equal to 0 to x equal to infinite. But the potential profile is such that between this region of x equal to 0 to x equal to L, the potential has a value of 0, and in the regions outside x equal to L and below x equal to 0, the potential has a value of infinite, which implies that the electron or the particle that we are considering has to have an infinite amount of potential energy in order to be located in these regions. Okay, it has to have an infinite amount of energy to be located in the regions outside this little valley, and this valley is what we call as the box. And as per this definition, this valley has got a length, or the size of the box is of length L, with the coordinate system being placed at x equal to 0 at this boundary and x equal to L being located at this boundary of the box. Now, since all these potentials are infinitely large, we say that the wave function, it is impossible for the particle to be present located in those regions, and for this example the particle remains very much confined to the box. Okay. So, the magnitude of the wave function, so since we are talking about the wave particle, the magnitude of the wave functions in these regions is 0, whereas the magnitude of the wave function or the nature of the wave function inside the box is what is to be determined. So, we can now write Schrodinger's equation for this example of a particle in a box and say that this is the kinetic energy, that is the potential energy, and that is the total energy, and for the region that is inside the box, the potential energy is 0. Okay. And therefore, Schrodinger's equation reduces to this simple form. And outside the box, as we mentioned, it is not possible for the particle to exist since it would require an infinite amount of energy, and we say that the wave function has got an amplitude of 0. Now, the general solution to an equation of a differential equation of this kind is given by defining the wave function as a summation of sines and cosines. So, we say that the wave function is a sine k into x plus b cosine k into x, where a is nothing but a constant coefficient and b is a constant coefficient and k is another coefficient that needs to be determined. Okay. So, from this point on we are going to apply the correct boundary conditions to try and define the wave function of the wave particle inside the box more accurately, and in particular we need to identify the parameters a, b and k. Now, k can also be seen to be related to the energy right from Schrodinger's equation. So, if we were to rewrite the differential equation as dou square psi by dou x square is equal to minus 2 m e by h bar square into psi, the value of k is related to the energy and it is 2 m e by h bar square. But we would now like to identify a further relation, okay, of k, particularly with regards to the geometry of the box, and then use that relation to identify the nature of the energy. Now, since this is a general solution, let us apply the property that the wave function must be continuous. Okay. So, this was the second property of the wave function that we discussed. Okay. So, which implies that if I were to consider these two boundaries, okay, which is there is some wave function here, okay, we do not know what the what the function is, but it must be continuous, which means that if I were to go to this boundary, okay, the value of the wave function just inside this edge must equal the value of the wave function outside this edge. Okay. And similarly, if you go to the other side, the value of the wave function inside this edge must equal the value of the wave function outside. And since we said that the wave function does not exist in this region, okay, the wave function is essentially 0. The probability of finding a particle outside this box is 0. So, that is the statement we made, and the argument was that the box is infinitely high. Okay. So, it is an insurmountable cliff. So, you have the wave function being 0 on the outsides, and therefore, the wave function at x equal to 0 must be equal to 0. So, that is the continuity, that is the continuous nature of the wave function. So, we first apply this condition that psi at x equal to 0 is 0. So, psi at x equal to 0 is a sine of k into x, which is 0, plus b cosine of k into x, which is 0. Okay. And this turns out to be 0 plus b is equal to the wave function at x equal to 0. And since this value, the wave function takes a value 0, we need this to be the first condition, which implies that my b is 0. Therefore, my wave function is of the form a sine of kx. So, for any x, since b is 0, the cosine term does not exist. So, this is the wave function. So, we have reduced the wave function from this very generic sine and cosine terms to just having a sinusoid term. So, now let us apply the boundary condition on the other side of the box, okay, which is at x equal to L. And at x equal to L, again we find that the wave function must be equal to 0, since the particle cannot exist on, or the wave particle cannot exist on the in the regions where x is greater than L. Now, applying that boundary condition at x equal to L, we say that this is the value or the magnitude of the wave function is 0 in at sine k L. Now, what are the possible solutions? We could have a to be equal to 0, but that would be a trivial solution, as it simply say that the wave function does not exist. So, we will ignore that solution, because we also have the possibility of a solution where k can be an integer times pi by L, okay, where n could be positive integers 1, 2, 3 and so on, and n pi by L into L is a integer times pi, and sign of an integer times pi is 0. Therefore, this wave function has now become more specific. We can define the wave function more clearly by applying the boundary condition at x equal to L and saying that the wave function is a sine of n pi by L into x. Now all that remains is to identify a. Using that value of k, so we have now identified b to be equal to 0, we have identified k to have the form of n pi by L, where n is an integer. So the wave function has now reduced from this very general expression of containing sines and cosines, it is now reduced to this. It has to be of the form of a sine n pi by L into x. Now the only thing that is left to be determined is a, and we do that by using the condition that the particle must exist somewhere, right. So if you remember, psi square was the probability density function for the particle, okay, and psi square dx is the probability that the particle exists between x and x plus dx. So therefore, the probability that the particle exists somewhere inside the box, we have already said that it does not exist outside the box, which implies that the particle must be existing inside the box. So the probability that the particle exists somewhere inside the box is basically the summation of all these little minuscule probabilities, which is simply the integral, simply stating that the integral from 0 to L of all these little probabilities is 1. Okay, so this is the probability that the particle exists somewhere inside the box, and that is guaranteed to be 1, okay, according to this experiment. So this is the next condition that your general psi must satisfy. So what does this become? So it implies that from 0 to L, if I take a square sine square n pi by L of x, then this must be equal to 1. Now you can write your sine square, okay. So let us say you have a general sine square alpha. You must note that cosine of 2 alpha is cos square alpha minus sine square alpha, or in other words it is 1 minus 2 sine square alpha. Therefore my sine square of any angle alpha is 1 minus cosine of 2 alpha by 2, okay. So we represent the sine square using this particular relation, and what that gives you is that this integral is nothing but a square 1 minus cosine of 2 n pi by L x, the whole thing divided by 2, and we need this to be equal to 1. We need this to be equal to 1, okay. Now this integral is simply a square by 2 into x, okay. So this is all with respect to dx, sorry I have missed that out. So you are integrating with respect to x everywhere. So this is the first term is going to be a square into 1 by 2 dx, which is a square x by 2, minus you have a square by 2 into your 2n pi by L into sine of 2n pi by L into x, okay. And the boundary conditions are from 0 to L. So the first term, if I apply these boundary conditions, it's this integral limit, sorry, these I'm not the boundary condition, sorry, I mean the limits of integration are from 0 to L. So if I apply these limits, okay, what do you get? The first term becomes a square by 2 into L, and 0 just results in 0. And the second term, when I throw in an L there, you should get minus a square by 2 into 2n pi by L sine of 2n pi. And when I throw in a 0 there, I just get a 0. So minus 0. Okay. So this entire term must be equal to 1. Now you see that since this is an even integer times pi, this sinusoid term will always be a 0. Okay. So therefore this term also vanishes. And you are only left with the fact that a square by 2 into L is 1, or a is equal to square root of 2 by L. So this is the outcome of applying this relation, that the probability of finding the particle somewhere inside the box is 1. Okay. So we can therefore describe the wave function. Okay. So now we have identified a to be square root of 2 by L, you identified b to be 0, and you identified k to be n pi by L, where n is an integer. So k could take multiple values and they are all integer multiples of pi by L. So therefore my psi is now become square root of 2 by L sine of n pi by L into x. So this is my wave function. So now we have identified, we set out on this exercise to try and identify a, b and k. We have identified all three terms and we now have our wave function. So what this says is that, firstly, note that the wave function has got a sinusoid term, and it must always end on the boundaries, it must always have a value of 0. Okay, so you will end up with a wave function looking like this, where at x equal to L by 2, if you take the case of n equal to 1, firstly, you will have sine of pi by L into x, and at x equal to L by 2, this value takes a value 1, which is the highest value. So you will find at n equal to 1, the wave function looks like this. At n equal to 2, I have sine of 2 pi by L into x. Okay. And at x equal to 0, at x equal to L, the value is definitely 0, but it is also 0 at x equal to L by 2. So if my n is equal to 2, so this was the n equal to 1 case. If n is equal to 2, at x equal to L by 2, my wave function again takes a value 0. The amplitude takes a value 0 because sine of 2 pi by L into L by 2 is simply sine of pi, which is again 0. But at x equal to L by 4, the amplitude is the highest. Okay. So you find that the wave function at n equal to 2 takes a shape of this kind, and you can continue drawing this, for n equal to 3, 4, 5, etc. So this is my wave function. All right. So that's the first point to note, that the wave function is sinusoidal inside this box. Now let's try to calculate the energy of this wave function. Okay, and that's going to tell you a lot of interesting things. How do we calculate the energy? So since my Schrodinger's equation is minus h square by 2m dou square psi by dou x square is equal to E psi, right? And now I know my psi accurately, so I'm going to use this expression in the left term here. So the left hand side will now become minus h square by 2m. Okay, the first derivative of this will yield square root of 2 by L into n pi by L of x into n pi by L into cosine of n pi by Lx. Okay, so if you look at what is d psi by dx, it is square root of 2 by L n pi by L cosine of n pi by Lx, and my d square psi by dx square is going to be minus square root of 2 by L into n pi by L whole square sine of n pi by L So we are going to use that term back here, which is there is going to be a minus sign because the derivative of cosine is minus sign, and that minus is going to cancel with this. So I will put a plus sign before this term into square root of 2 by L into n pi by L squared sine of n pi by L into x. So that is the left hand side, and you will notice that this term here, which is square root of 2 by L into this sign, is nothing but your wave function sign. Okay. So you might as well just write these two terms, get rid of these two terms and just use psi here, and this is equal to E psi. Okay. Now which means that my total energy is given by this expression here, which is n square pi square by L square h bar square by 2m is my energy for the when n takes a value, where n takes only integer values. Okay. So this is the energy for some particular n. Now the first thing which you notice here is that the energy cannot take any arbitrary value, since n can only be integers. Okay. So if my n is 1, my energy is pi square h square by 2m L square. If n is 2, my energy is 4 pi square h bar square by 2 ml squared, and so on. So the first thing to note is that the energy is quantized. Okay. You can't have this particle having an energy of let us say something in between. So it can't have something like 1.5 pi square h bar square by 2 ml square, because that violates the condition that n has to be an integer. Okay. So that can't happen. All right. So the first thing to note is that the energies are all quantized. Okay. The second thing to note is that the energy is very strongly dependent on the size of the box. It varies as 1 by L square. So if you were to take a relation, y is equal to 1 by L square and see how does y vary with L, you will see it is quite dramatic. As L approaches 0, y climbs up very large, and as L starts increasing, it completely comes down. It reduces very quickly. Okay. So this dependence on 1 by L square is quite dramatic. So which means that if I have a box that is very narrow, then the energy of the particle is very large, and the moment I start increasing the width of my box, the energy of the particle drops down. Okay. So let's note down these facts very neatly. Do forgive my reuse of the slide again and again. Okay. So the first point we noted was that energy is quantized. Okay. The second is that a small box implies large energy for the particle, and a large box implies small energy for the particle. So the energy scales is 1 by L square. Now let us also look at the mass. If the mass of the particle increases, then my energy decreases. Okay. So these are all the absolute values of the energy. Okay. But if I were to draw all the different energy levels, okay, like as it's shown here. So this is at n equal to 1, this was my wave function. At n equal to 2, that is my energy. At n equal to 3, there is another energy level, and so on and so forth. Okay. Now if I were to draw all the energies and measure the distance or the energy gap between two subsequent levels, okay, which is essentially En minus En minus 1. Okay, and now I am looking at the delta En, okay, which is the energy difference between two subsequent energy levels. Now according to this, it should be pi square h bar square by 2m L square into n square minus n minus 1 squared. Okay, and if you were to just look at this expression, it is nothing but 2n plus 1. I'm sorry, 2n minus 1. Okay. So the gaps between these, which is my delta E, okay, scales as 2n minus 1 into pi square h bar square by 2m L square. So the first thing to notice is as n increases, the gaps between these two subsequent energy levels also increase. So here you have a smaller gap, and there you have a larger gap, and n keeps increasing, this gap will keep increasing. Now the second thing to note is that as L or M increase, the gaps will reduce. Okay, so for a large box, not only is their total energy small, the energy gaps between two subsequent energy levels is also small, okay, for a large box. And similarly, the energy gap between two successive energy levels for a large particle with a large mass is also small. And that is why when you have large bodies with large masses, okay, so even though they are composed of many particles, if you avoid that, if you just set that aside, you know, let us say it's all coherent, and let's say it's just like behaves like one discrete large particle. The spacing between the energies is so small that this massive entity can take almost any energy it likes, okay, and therefore you never get the feeling of something being quantized in your day-to-day experiences. So if you were to take a billiard ball or a tennis ball and throw it, you find that depending on the amount of energy you throw in, classical mechanics tells you that it can always take any energy you like, depending on how much energy you throw into it. Okay, now that's not true in fact. So what this experiment is telling you is that if it's a discrete particle, okay, if you imagine even this large mass to be one particle, as the mass increases, it would appear, it would give you the illusion that the energies could be almost smooth and continuous, but in reality it is not. And the difference, it's always discrete, and that difference between two energy levels is given by this particular term here, which we looked at, this particular term. Okay. And similarly, if the size of the box starts growing very large, the energy levels become very, very fine. Okay. So let's so this is an important message as well. So not only is the energy going to reduce, the energy spacing going to reduce with the mass of the particle, but if I were to increase the size of the box and you look at all these energy levels, you will find that the energy levels are much more closer to each other here. Okay, because once again the difference in two consecutive energy levels varies as 1 by L square. So if we think about the electron, so how does this connect with our semiconductor physics? So if you were to think about the electron, okay, and let's say it's sitting in some material, okay, and it's sitting inside a potential well which can resemble this box, and in fact there does exist such a potential well, which is the nucleus of the atom. So if you think about the nuclei, it's got, let's say, positive charge, and therefore it's got a certain electrostatic potential, and the only thing is it's not shaped like a box, but the electron is in some sense held inside this potential well. So if you were to imagine all this as a box, okay, and if you look at the amount the electron is allowed to move about around this nuclei, and if you sort of imagine an effective length or the effective size of the box to be that, then the energy levels the electron can take, okay, so in a material in which the electron is more or less free, is much more finely spaced as compared to an electron which is not so free. Okay. Now let us sort of extend this idea, we will sort of generalize this idea to a 2D case. Okay. So let us say the particle is not sitting inside a one dimensional box, but it is sitting inside a two dimensional box, and we will still retain the fact that the particle sees an infinite cliff. Okay. So you can sort of imagine a 2D box, and for the time being I will draw a rectangular box, okay, for mathematical conveniences I will show you. So let us imagine a rectangular box. So it's a two dimensional drawing here. It's a, so on the z axis you have potential. Okay, so let's call that y and let's call this x. So initially we only looked at that as a 1D case, okay, where the distance was only in one direction, but now you have a two-dimensional distance plane. Okay, so this could be Lx. So let's call the width of the box in the x direction as Lx and the width of the box in the y direction as Ly. Okay, so it goes from 0 to Ly. So if I were to draw the coordinates, this would be my coordinate system. So that's Lx comma 0 and that is 0 comma Ly and this is 0 comma 0. So let this be my coordinate system. So I'm only looking at the floor now. And if I were, since my potential is on the y axis, the potential of this floor of this box is 0. And the potential over here, which is outside in the regions outside this box, okay, so it's a hollow box and there is space all around it, and that potential is infinitely tall. Okay, so this is infinitely high. These are all infinitely tall walls, and there is this little hollow which is sitting at 0 potential, and it's got a length x in the x direction, Lx in the x direction, a length Ly in the y direction. So that's the situation. I probably should have had a nice drawing here, but if you can understand this drawing of mine, you have the situation in place. So we want to solve Schrodinger's equation for this case. Okay. Now since I chose a nice little rectangular box, I can use one simple trick, which is I can say that my psi can be written as a product of two components, the psi in the x direction and the psi in the y direction. Okay. So let us say my psi, my wave function for the particle, can be written as a product of the wave function in the x direction and the product of the wave function in the y direction. So if I were to use this relation right here, my Schrodinger's equation, which now has got two terms, because you now have to consider the potential, the momentum in the x direction and the momentum in the y direction. So it's got the x and y aspects to it, and that's my total energy. My potential is still 0. Okay, so it's just Schrodinger's equation but written out in the 2D case, and it's still a time independent Schrodinger's equation. Now if I were to use this particular condition in my Schrodinger's equation, I will end up with dou square psi x psi y by dou x square plus dou square psi x psi y by dou y square is equal to E psi x psi y. Okay. Now psi x is purely dependent on x and psi y is purely a function of y. Okay, so this is not a function of x and that's not a function of y. So which means that as far as this derivative is concerned, psi y is just a constant coefficient. Okay, so you can put that outside the derivative. And as far as this derivative is concerned, psi x is a constant coefficient and you can place it outside. Okay, so that's my differential equation. So now let me divide throughout by psi x psi y. Okay, now E is a constant coefficient and therefore I end up with minus h square by 2m, and I'm going to divide throughout by psi x psi y, 1 by psi x dou square psi x by dou x square plus 1 by psi y dou square psi y by dou y square is equal to a constant which is energy. Okay. So if you look at this particular term here, it's got 1 by psi x and it's dou square psi x by dou x square. There is no y component at all. There is no psi y, there is no y. Okay. So this parameter here is not at all influenced if you play around with the y aspects of the box. So, if I say increase or decrease Ly, this first term here should not be should not matter to this term at all. And similarly, the second term here is purely a function of y only, okay, and it should not matter to it as to what is happening in the x direction. And because this is the case, I can rewrite my energy as having two components. One is the energy in the x and the other is the energy in the y. And I can split this in such a way that I can rewrite this one equation as two separate equations because I have got the same message. Okay, I can write this as, this is the first term of your, this is the first term on the left hand side, and that is equal to Ex, and let us say minus h square by 2m 1 by psi y dou square psi y by dou y square is equal to Ey. So, let us write this equation, split it into these two terms. Okay. If I were to take this psi x to the other side, I end up with the equations looking that way. If I take the psi x and psi y to this side, these are my equations. Now, these two are your very familiar set of equations which you saw for the particle in a 1D box. And therefore, you can solve these two Schrodinger's equations independently. Okay, so, you can now solve these two Schrodinger's equations independently and say that my psi x has got a function, a wave function that the psi x looks very similar to what you saw before. It should be of this form, square root of 2 by Lx sine of nx by Lx pi by Lx into x, and psi y will be of the form square root of 2 by Ly sine of n pi by n y pi by Ly into y. Okay. So, this is psi x, it depends on the length of the box in the x direction, and it depends on a quantum number or a integer nx. And on this side you have the psi y depending on the length of the box in the y direction and another quantum number or an integer ny to satisfy all the boundary conditions. And the total wave function is simply the product of these two, which can now be written as psi x into psi y. Okay, so, the total wave function is psi x into psi y, which is square root of 2 by Lx square root of 2 by Ly into the product of the two sinusoid terms, sine of nx pi by L into x sine of ny pi by Ly into y. So, this is the solution of Schrodinger's equation in a two dimensional box. Okay. So, it was convenient for us to separate these two terms. Okay. Now, that may not always be possible. So, for example, if you have so here the coordinate system I chose, it was a rectangular box. Okay. And in a rectangular box the x and y directions were orthogonal components. If you look at the basis vectors, I have chosen two orthogonal components there. Now, if you had a box, say it was shaped as a triangle, probably not so obvious. Okay. But nevertheless, just to illustrate this point, I think this is a good message.